This is my analysis of homework 2. So starting at problem 1, first off we had to import Qiskit libraries, and problem 1 focused on quantum circuit implementation of a 6-bit superdense coding. To do this, I defined 3 helper functions. One generates a bell state using applying a Hadamard and then a controlled NOT gate. The second one encodes classical bits to Alice's qubits. So if the least significant bit is a 1, then it will apply an X gate to Alice's qubit, and if the most significant bit is a 1, then it will apply a Z gate to Alice's qubit. The third helper function is to decode the bell state to perform measurement, and to do that we had to do the inverse of the bell pair. So it applies the C0 gate first and then the Hadamard. The function itself to create a 6-bit superdense coding accepts a string of length 6, and that's composed of binary elements. It first divides the 6-bit string into three 2-bit strings, where pair 0 is assigned to B5 and B4. Pair 1 is assigned to B3 and B2, and pair 2 is assigned to B1 and B0. After dividing the 6-bit string into 3 2-bit pairs, we set up the registers. We'll have 6 quantum registers and 3 classical registers. So we'll have 6 qubits, and we will have 3 classical registers, 1 for each pair of 2 bits. So classical register 0 will correspond to bits 5 and 4, and so forth. Our quantum circuit is comprised of both these quantum and classical registers. The first step was to create 3 entangled bell states, and for Alice to encode each pair of classical bits onto each of her corresponding qubits. Then Alice will send her qubits to Bob, where Bob will perform decoding and bell measurements. Here, for each measurement, Alice's qubits corresponds to the most significant bit, and Bob's qubit will correspond to the least significant bit. Then this loop will loop over all 64 combinations of 6-bit messages, so all binary strings of length 6. It will start by listing all possible combinations, and for each message in these, it will create the superdense circuit, and it will run a quantum simulator and measure each result. It will find the most frequent outcome and reconstruct the recovered messages by parsing these outcomes into pairs, and the recovered messages is a concatenation of these pairs, and then it's reversed. The spaces, because of this concatenation, are then removed. An assertion message is here to assert that the message actually inputted into the superdense circuit is what we recovered. This is a picture of the circuit diagram. For question 2, I was tasked with implementing 3 qubit teleportation, and to teleport 3 qubits, we need 6 auxiliary qubits, or 3 entangled pairs shared between Alice and Bob. So we'll have a total of 9 quantum registers, and for each qubit that we want to teleport, we need 2 classical bits. So we'll have a total of 6 classical registers. The first step is to prepare an arbitrary state to teleport. I chose the GHT state. And the second step is to create 3 pairs of bell states that will be shared between Alice and Bob's. using, like before, the Hadamard and then the control knot, with the control being on Alice's cubit and the target being on Bob's cubit. Bell measurement will then be done on each of these and stored into a classical bit. Here we are decoding, so we're doing the inverse of this circuit and then performing the measurement. Then there is corrections done on Bob's qubit. So if the qubit that is stored in the first classical bit, if it's a 1, then it will apply an X gate to Bob's first qubit or qubit 6. And if the qubit that's stored in the 0 register is a 1, then it will apply a Z gate to this first qubit. So these are doing corrections on Bob's qubit, where C1 and C0 correspond to Q3 and Q0. Corrections are then done on Bob's second qubit and Bob's third qubit similarly, and then the circuit is returned. Here is a circuit diagram where you can see the state preparation here. This is the arbitrary state. And then we produced the 3 pairs of entangled qubits, and we perform the decoding of the Bell entanglement so that we can conduct measurement on each one of these, and we do the corrections here. Thank you.